Welcome to this lesson on interference and wave superposition. Interference is one of the most fascinating phenomena in the study of light and optics. It demonstrates the wave nature of light and helps us understand how waves interact with each other to create beautiful and complex patterns. In this video, we'll explore how light waves combine and what happens when they meet. Let's start with the basics. What exactly is wave superposition? When two or more waves overlap in the same region of space, they don't bounce off each other or push each other away. Instead, they combine to form a new wave pattern. This process of overlapping and combining is called superposition. Think of it like two ripples meeting on the surface of water. They pass through each other and create a new pattern where they meet. The principle of superposition gives us a mathematical way to understand this combination. It states that the resultant displacement equals y1 plus y2. In simpler terms, when waves overlap, the total displacement at any point is simply the algebraic sum of the individual wave displacements. This means we add the heights or amplitudes of the individual waves together, taking into account whether they are positive or negative. Now let's look at constructive interference. This occurs when two waves meet in phase, meaning their crests align with crests and troughs align with troughs. When this happens, the waves' amplitudes add together, creating a larger combined wave. The result is maximum brightness or intensity in the case of light waves. Imagine two friends pushing a swing at the same time in the same direction. The swing goes higher. That's constructive interference in action. There's a specific condition for constructive interference to occur. The path difference, delta x, must equal n lambda, where n is 0, 1, 2, 3, and so on, any whole number. Lambda represents the wavelength of the light. This means the waves must be separated by a distance that is a whole number multiple of the wavelength for their crests and troughs to perfectly align and reinforce each other. On the other hand, we have destructive interference. This happens when two waves meet out of phase, meaning the crest of one wave aligns with the trough of another wave. In this case, the waves cancel each other out because their amplitudes subtract from one another. The result is minimum brightness or even complete darkness in the case of light. It's like two people pushing a swing in opposite directions at the same time. The swing barely moves. For destructive interference to occur, there's also a specific path difference condition. The path difference, delta x, must equal the quantity n plus 1/2, all multiplied by lambda. Here, n again represents 0, 1, 2, 3, and so on. This formula tells us that the waves must be separated by an odd multiple of half wavelengths. This ensures that crests meet troughs, causing the waves to cancel each other out. When we observe interference in practice, we see interference patterns. These patterns consist of alternating bright fringes and dark fringes. Bright fringes appear where constructive interference occurs, creating regions of maximum light intensity. Dark fringes appear where destructive interference occurs, creating regions of minimum or zero light intensity. These alternating light and dark bands form the characteristic interference pattern that beautifully demonstrates the wave nature of light.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.